Hello everyone, good time. I hope you are all doing fine. Today we are going to look at one example and solve it during the recitation hour. Usually solving this example takes time because the students ask questions during the class, but in this situation that we solve the examples as a recording file, I will leave some minutes at the end of the presentation and at the end of the class for you to solve the example at home, and then make sure you follow the steps correctly and kind of pay attention to the small and important points that we have about the stress distributions. If you have any question, I'm available after this recording. Just send me an email and we can definitely discuss your issue or the question through email, or we can schedule a time for WebEx meeting and discuss that over there. But I'm going to explain this example. We are going to solve it together, and then after this I want you to repeat solving it at home, and if you have any question, let me know, we can discuss it. So in this example, you can see the problem is asking us to find the stress at the reinforcement level in the reinforced concrete section below, and this is the section that we are talking about. You can see the dimensions are given, and then you can see the bending moment that is applied to the section is positive bending, which means it is putting top of the section in compression and bottom of the section in tension. In general, the definition of positive and negative bending returns to the convention that we had in statics and structural analysis. If I want to remind you about that, let's say this is a beam, and then the applied moment looks like this. So with this direction of bending moments, as you can see, top of the beam will be in compression and bottom of the beam will be in tension. If I want to show you the deflected shape, of course it is exaggerated, but the deflected shape looks like this. I hope it is clear for you to follow, but this is the deflected shape of the beam. When we are applying positive bending, the deflected shape is like this. Top of the beam is in compression and bottom of the beam is in tension. Over here we have compression and over here we have tension. Without this knowledge, if I just wanted to look at the section alone, and if, for example, these bending moments were given to us without having such a thing in the example, by default, we know that for such a section, bottom of the section will be in tension, top of the section will be in compression, because reinforcement is over here, and we know in concrete sections, we always put the reinforcement in the tensile region. Of course, we have double reinforced sections, which we will talk about later. But if I see a situation like this, for example, a section like this, where reinforcement is over here, it means that this side is in compression and this side is in tension. So this is the section. You can see the dimensions, and then we also have 1, 2, 3, 4, and 5 number 8 bars at the bottom of the section, and these are located 2 inches from the very bottom of the section. And the question is asking about finding the stress at the level of reinforcement. At this level, when the applied moment is equal to 50 kip-foot, then the amount of moment is increased to 100 kip-foot, and then it is asking about finding the ultimate strength of the section, or MN. As you remember, during the second chapter, when we were talking about stages that we have in the behavior of reinforced concrete sections, we said that we have uncracked section, we have cracked section, and at the end we have the ultimate strength stage, which the section is basically reaching its ultimate strength. So let's see how we can find the stress for this situation where moment is equal to 50 kip. As you know, at the very beginning, what I need to do is to consider the cracking moment and see if the applied moment is greater than cracking moment or smaller than cracking moment. Or in other terms, we have to understand if the section has cracked under the applied load or not, because that is very important in terms of finding the section properties, whether the section has cracked or not, gross section or transformed section, and how should I consider the stress distribution. The strain distribution is always the same. Stress distribution depends on the stage of behavior. So I have to calculate the cracking moment and then compare the applied moment versus cracking moment. For cracking moment, the basic equation that we have for that is coming from this simple equation that we have for flexural analysis. Flexural stress is equal to M multiplied by C over I. C is distance from neutral axis. So moment will be stress multiplied by I over C. For the case of cracking moment, this stress will be Fr, tensile strength of concrete, because concrete cracks where it is in tension, so it should be tensile strength of concrete, or Fr. I should be Ig. Gross section properties, as we discussed in the second chapter, and C is the distance from the very tensile level, in this case bottommost distance of the section to the neutral axis. C is that distance. As you can see, with this idea, if I don't kind of remember the actual equation, with just the knowledge that I have from strength of material, I can come up and remember the equation that we had for cracking moment. This is the equation, and as you can see, Yt is the distance from neutral axis of the gross section to the tensile region that we are looking at. So with this being said, let's calculate the cracking moment, and that is calculated over here. As you can see, the equation is over here. The things that I need to calculate over here are Ig, gross section properties, which is the moment of inertia of the gross section, and Yt is the distance from neutral axis to the tensile region. When we are talking about gross section properties, we are basically looking at the section that we have without the reinforcement. Just the section, the concrete section itself without the reinforcement. That is the gross section. As you can see, this is the section, the gross section, and at the very beginning I have to find the centroid of this section, because that will work, and that will be the neutral axis. So for finding the centroid of this section, this is the very basic equation that we have for that. That is from, we talked about it, I believe, even in the high school physics, the basic equation. But from strength of material, we know this is how to find centroid of geometrical shapes. Summation of each shape that we have in the section multiplied by its own centroid from one origin point, and then dividing it by summation of areas. Over here I'm considering two shapes. Let's say this is one shape, and then this is the other shape. For this shape, this bigger square or triangle that we have, I'm sorry, bigger rectangle that we have at the bottom, the width is equal to 6 plus 8 plus 6, 20. So this side is 20, and then the height is equal to, as you can see, 18 inches. So the area is 18 by 20, and then the distance from centroid of this shape to the origin, I'm assuming this bottom level as origin. So this bottom region or this line is the origin which I'm calculating all the distances from. And then at the end, the neutral axis or the centroid that I find, or y bar, is the distance from that line to this origin that I'm considering. You can consider it at any other point in the figure, but you have to just make sure you calculate all the distances from that origin or reference line or reference point in cases where you need to find the two coordinations of the center point. In this case, on one direction, we can see the shape is symmetric. Just in the vertical direction, we can see it is not symmetric. That's why we need to find the centroid. So I consider this line as the origin line, and now I'm going to consider the distance or the centroid of each of these shapes that I talked about. This bottom square and this bottom rectangle and top rectangle, the centroid of each of these shapes to this origin point. The first shape, we talked about the dimensions. The distance is just centroid of this shape to the origin, which is 18 divided by 2, because this side is 18, and then the centroid of this shape, this bottom rectangle, is equal to 18 over 2, or 9 inches. So 9 inches is the distance of this shape. Then we have to look at this top rectangle. Dimensions are 6 by 8, and then the distance is the distance of its centroid to the very bottom line. That will be 18, this distance, plus this small distance, which is 6 divided by 2. As you can see, this is 6. So this centroid is at 6 inches from this line, and 6 plus 18 inches from the very bottom. So let me clean the things that I added to the file, and then we can move forward. So putting these over here, these are at the top of this ratio, and then at the bottom is just summation of areas. Calculating these, y bar is equal to 10.41. That is the centroid of this shape from this bottom line. Ig is the moment of inertia of this shape, and we know for a section or for a situation like this, that will be the moment of inertia of each of the shapes that we have around themselves, multiplied by the area, multiplied by the distance from the centroid of each of those separate shapes to the centroid of the whole section to the power 2. So we said we have two shapes over here. One is this one, and the other one was this top one, or top rectangle. So the centroid of each triangle, let's say this is a triangle, and the centroid of this triangle about its own, the moment of inertia of this triangle about its own centroid, which is right at the middle of it, is equal to b h cubed over 12, right? That is when I'm calculating the moment of inertia about the centroid. If I want to calculate the moment of inertia, for example, about this line, at the bottom of it, then I have to say bh cubed over 12 plus a d squared. A is the total area of this shape, which is b multiplied by h, and d is the distance from its centroid to the line where we are calculating the centroid about. That is the major rule or the basic rule that we have when we are calculating the moment of inertia about different lines or different regions other than the centroid of the shape. So area multiplied by the distance from centroid of the shape to the place where we are calculating the moment of inertia about. So with this knowledge, I can calculate the total moment of inertia of this section. First, we have this bigger rectangle that is 20, this side multiplied by 18 cubed over 12, and then multiplied by area of this shape, which is 20 by 18, multiplied by the distance that we have from centroid of this lower rectangle to the centroid of the whole shape, which was 10.41 inches from the bottom. So the centroid of the shape is located at 9 inches from the bottom, and the distance from these two will be just this number, and that should be squared based on the equation that we have over here. So that is for this shape, it is done, and now I have to calculate for this top rectangle. That is 8 multiplied by 6. 8 is this width and 6 is this height. So 8 multiplied by 6 cubed over 12 added or plus 8 multiplied by 6 area multiplied by the distance of the centroid of this shape to the centroid of the whole shape. That will be 6 over 2 plus 18 minus y bar. You can calculate it in different ways, but what I need to put in this parenthesis over here is just this distance. So I calculated the distance to the very bottom and then subtracted y bar. That will be this distance over here. So putting that over here, you can see the moment of inertia that we can get for the whole shape by adding these terms will be 15,962.8 inch to the power 4. And then what I need to do is to just return this to the equation that we have over here. IG is calculated, YT is the distance from centroid to the tension face, that is this distance, which is the same y bar that we calculated. All I need to calculate is FR right now because everything else is calculated, and FR will be 7.5 square root of F prime C. Of course, if you look at the first presentation or the first chapter when we were talking about properties of concrete, there was a lambda over here, but we said since we are always dealing with normal weight concrete, lambda is always equal to 1. Excuse me. So putting F prime C that is given as properties of the material 4500, putting that in the equation, you can see the FR is 503 or about 500 psi. That is the tensile strength of concrete, specifically this concrete with 4500 psi as the compressive strength. So that is tensile strength, and now I can return it to this equation, calculating the ratio. The final value will be in terms of pound and inch. Pay attention to the units. FR was in psi, IG or moment of inertia was inch to the power 4, YT was inch. So calculating this, the units will be pound inch. It is not common to mention and kind of describe moments in pound inch unit, so we have to change it to keep foot, and for that I have to just divide it by 12,000. And if I do that, we can see the cracking moment is about 64 keep foot. So now we can look at the question and compare the applied moment versus the cracking moment. In the first situation, applied moment is 50, cracking moment was 64, so the applied moment is lower than the cracking moment, right? So with that being said, I can simply consider the situation of having a section with applied moment lower than cracking moment, and then we know the stress distribution is linear. So all I need to do is to just consider the equation that we have for stresses, and that is the equation. Pay attention to this n. That is because we have composite material, and whenever we have composite, I mean multiple materials in one section, we have to consider n, which is the ratio of the ratio of Young modulus of the materials. Over here we have steel and concrete, so n is ES, Young modulus of steel, over Young modulus of concrete. Young modulus of steel is this number, and it is the same all the time because we know that is the major property of steel materials. Young modulus is the same regardless of different grades or strength values. So 2.9 to the multiplied by 10 to the power 7 psi is the Young modulus of steel. Young modulus of concrete is 57,000 multiplied by square root of f prime c. We learned about it in the first chapter. Putting f prime c, we can see n is equal to 7.58. So I have to just return n to this equation. Stress is equal to m multiplied by distance over I. I is Ig because in this situation, section is not cracked, and that's why I am using Ig or gross section properties in the equation. So over here I have n, I have Ig, I have distance from steel to the neutral axis. We calculated this neutral axis. As you can see, it was located as 10.41 inches from the bottom, but reinforcement is located a little bit higher than the very bottom. And if we go and look at the configuration of the shape, you can see it is 2 inches from the bottom. So this distance is 10.41 total distance minus the distance that we have from the reinforcement to the bottom. So with those, we can simply calculate this stress in steel, and as you can see, that is about 2,396 psi, about 2.4 ksi. That is the stress in steel. Now we can move to the second part, where it is asking about a situation of having moment equal to 100 kPa. Now in this situation, you can see the cracking moment was 64 and the applied moment is 100. So the section has cracked under the applied moment, and now I have to consider the properties of cracked section. As you can see over here, I'm considering the cracked section. This is the stress distribution, and these are important information that we need for solving the problem whenever the section is cracked. The first step is to calculate the properties of cracked section, which means I have to find the neutral axis, the location of this line, and also I have to need to calculate the moment of inertia of this section, which is cracked section. So for finding this, we have to calculate the moments of different areas that we have in the shape, and the moments on one side should be equal to the moments of the other side. So in this side, I have two rectangles, this bigger one and that smaller one in the top. So as you can see, the moments because of those are calculated over here. The first term is the moment because of this one, that is 6 by 8 the area multiplied by y1. I don't know its value, so that's why I'm just considering some parameter. We will find it, and once we find it, we know the location of neutral axis. So the distance from this centroid to the neutral axis is 3 plus y1, And then we have this bottom shape, and for that bottom shape the distance is just y bar and y1 divided by 2. Area is y1 divided by multiplied by the width, and this width is equal to 20, and then the distance from centroid of this bottom rectangle to the neutral axis is y1 divided by 2. So these are on one side of the neutral axis. The things that we have on the other side is just a steel. So I have to calculate the transformed area, that is n multiplied by AS. AS is 5 number 8. If you look at the table that we had in the first chapter, area of number 8 is equal to 0.79. We had 5 reinforcement over here, so number of reinforcement multiplied by area of each, and then this n is the n that we calculated, and that is the ratio of Young modulus of steel over Young modulus of concrete. So calculating those, that is the only thing that we have on the other side. Excuse me. So over here you can see on the other side we have the reinforcement or steel, and I have to just calculate the moment of area that we have on the other side. So that is the amount of steel area that I have, that is 5 multiplied by 0.79. This n that I have over here is the ratio of steel, Young modulus of steel over Young modulus of concrete. And then the only thing that I need to include is the distance from this steel that we have to the neutral axis. That is the distance from the very top, which is equal to 16 minus y bar. That's the distance that I have over here. So now that we have this equation, I can simply look at the equation that we have over here, and then the only unknown in this equation is y1. So I can calculate that, and you can see this parameter, or y1, is equal to two values, because we have a parabolic equation. The negative value is meaningless. The positive value is the value that is the useful value for us. So based on this, y1 is about 3 inches, 3.8, but we can accept 3 inches. Now that is y1, and now I know the location of neutral axis in the transformed section. Now I can calculate the moment of inertia of this cracked section. The procedure is the same. All I need to do is to just use the equations that I showed you earlier. That is this equation. The only difference that we have in the cracked section is the configuration of the section, but the equation that we need to follow is the same. So as you can see over here, I calculated the moment of inertia of transformed section, or this section that we have over here. We have this top rectangle, moment of inertia excuse me, of this shape about itself or about its centroid is equal to 6 by 8, this side, multiplied by 6, which is height cubed over 12. And then I have to multiply this area, or this term, this area of the shape, by the distance that we have from centroid of the shape to the line where we are calculating the moment of inertia about. So that is this distance. As you can see, this top portion of this distance is 3. that is just 6 divided by 2, and over here we have the y1 value, which is 3 inches, and that's why we have this in the parentheses, or this distance in the parentheses. So let's look at the other shape that we have, and that shape is this bottom rectangle. For this, I can follow the same equation. Just say, for example, this width, which is 20, multiplied by the y1 that we have, and that is 3 inch, cubed over 12, plus the distance that we have from centroid of the shape to the neutral axis, and that will be y1 divided by 2, or 3 divided by 2. That's one way. The other way is to consider this. And this equation, b multiplied by h cubed over 3, is the moment of inertia of rectangular shapes about the bottom line. Instead of calculating it about the centroid, it's about bottom line. If you want, you can simply derive this by looking at the shape. You know, when we were looking at the centroid of the shape itself, the moment of inertia was bh cubed over 12. And now if I want to calculate it about this bottom line, I have to add this term, area multiplied by d to the power 2. A is equal to bh, and d is equal to h over 2, and now it should be squared. If you calculate this term over here, that is basically bh cubed over 4. So bh cubed over 4 is the additional term, bh cubed over 12 is the initial term. Adding these two together, the final result will be bh cubed over 3. Right? You can simply calculate it on a paper and see how I used this term for this rectangle that we have over here. So moment of inertia of this rectangle about this bottom line is basically b, or 20, multiplied by y1 3 cubed over 3. That will be the moment of inertia about this bottom line. So that is calculated. All I need to include is the moment of inertia of this steel that I have over here. That is the area, which is NAS. Make sure to always include that N, which is ratio of Young moduluses. And then AS is just 5 number 8. And then the distance that we have from this to the neutral axis, that is 16 minus y1 or 3 squared. If you calculate this, you can see the cracking, or the cracked section moment of inertia is equal to 7,100. If you compare this value with IG, excuse me, or gross section moment of inertia, you can see the value has decreased a lot. That's because section is cracked and part of the section is gone. So the moment of inertia has decreased from about 16,000 to 7,100. That is something that we can quickly check during the solution and kind of understand that if the values that we are getting are making sense or not. So I can put this cracked section moment of inertia into this equation and find the stress in steel when the applied moment is 100, or when the applied moment is greater than the cracking moment. And we calculated it before. Moment is 100, keep foot, changing it to pound and inch because the I, or the moment of inertia that we have is in units of inch. And then I have to just include y, the distance from this steel to the neutral axis, that was 16 minus 3. And then once you do that, you can find the final value as 16,000.6 psi, or about 17 ksi. So that was the second part of the question, and now we can look at the third part, which is finding the ultimate strength of the section. As you know, when we were talking about the ultimate strength, we are referring to a certain shape of a stress distribution in the section, and in that specific shape we have a rectangular block as the compressive stress, and stress in steel is equal to Fy. That was the ultimate stress distribution or ultimate strength stage. If you want, you can go back and look at the discussion that we had in the second chapter. In the last portion of it, we were talking about ultimate strength. To just quickly review that, I can show you the typical section that we have. Let's say reinforcement is over here. If I want to look at the stress distribution, it looks like this. Let's say we have the neutral axis over here. We said concrete at this stage is showing a nonlinear stress distribution, something like this. On the tensile region, concrete is gone because it is definitely cracked. And we have this tension force in steel. T is equal to AS multiplied by Fy, because this steel at ultimate strength has yielded. The only thing is that this nonlinear shape of concrete, and we said to simplify this situation, we are going to replace it with a rectangular shape, something like this. The intensity of stress in this rectangular shape will be this value is equal to 0.85 F prime C. This maximum stress for the actual stress distribution is F prime C, but this is nonlinear. That's why we replaced it with this rectangular shape. The intensity of stress in this shape is equal to 0.85 F prime C, and the depth of it is a bit lower than the actual stress distribution. That is A, and that is what we need to calculate based on equilibrium of tension and compressive force that we have in the section. If you want, you can go back and look at the discussion that we had in the presentation files, but over here I'm showing you the stress distribution at ultimate strength of the section. As you can see, this is the neutral axis. As we increase the amount of load, the cracks will be larger and wider. That's why the neutral axis is moving up as we increase the load. This is the stress block in the compression region, and then total A that I'm showing you is the depth of compression block, and then T is the tensile force that we have in steel, and that is AS multiplied by Fy. For finding Mn or ultimate strength, I have to calculate the moment because of these forces, and the easiest way is to calculate the moment because of tension force about compression force. That will be T multiplied by this distance, the distance from forces. And we can calculate that later based on finding the location of C or the centroid of this compression block. But let's see how can I find A or the depth of this compression block at the top. Excuse me. I know we have equilibrium in the section, which means this tension is equal to compression. Tension is equal to AS, area of steel, multiplied by Fy, yield strength. This value Fy is given. If I scroll up, you can see Fy is given as 50,000. So I'm going to use that in my calculation. That is over here, Fy. That is the tension force. And now for the compression force, I have to calculate the area under this compression block, which is this area, and multiply it by the intensity of the stress, which is 0.85 F 0.85 F prime C. The intensity of the stress is just something based on the idea of ultimate strength. That is always the same. What is changing is this A, or depth of compression block, which depends on the amount of tension force and the configuration of the section. So I'm calculating the amount of compression force that we have by multiplying the stress by the area under the stress. The area, as you can see, because of the configuration of the section, is one rectangle over there, or this rectangle at the top, and this smaller rectangle at the bottom. The thing is that since we don't know the depth of compression block, we don't know if this line is extended to the bottom rectangle, or it might be a situation like this, just having portion of the top rectangle, and maybe just that area would be large enough to balance the tension force that we have over here. I don't know this. That's why at this situation, I'm going to assume the compression block is extended to the lower rectangle. I'm going to continue the solution by this assumption. If I get a negative value as A1, it means my assumption is wrong. If I get a positive value for A1, it means that my assumption is right and compression block is extended to the lower rectangle. So based on this, I'm going to calculate the compression force based on multiplying the stress by this area that we have over here. The first area is just this top rectangle, that is 8 by 6, and this bottom one is A1, the value that we don't know. We don't know how much it is extended to the bottom portion of the section, multiplied by width, this width, which is 20 inches. So based on that, I'm going to consider equilibrium. This force is equal to this force. As you can see, the only unknown is A1, and once we do that, A1 will be 0.18 inches. As you can see, the compression block is just extended a little bit below this top rectangle. If, for example, the steel was a bit lower than what we have in the section, we wouldn't see the situation like this. The compression block would be just in the top rectangle, and it wouldn't be extended to the lower portion of the section. So in that situation, the A1 that I would get would be negative, and then I should have returned back and return to this situation and just consider the compression block in the top portion alone, and then find A directly by saying C is equal to 0.85 F prime C multiplied by 8 multiplied by A1. Just an area in the top portion of the section, and then that A1 should be smaller than total depth that we have over here, which is 6. But that is the situation of having compression blocks just in top portion of the section, or in this top rectangle. So we could find A1, and now I can calculate the centroid of this shape that we have over here, because that centroid is the place where this compression force is applied. The compression force is basically the compression that we have because of this stress in this area, and that is located at the centroid of this shape, which should be some point like this. Some point like this. So A bar, this is the centroid of this shape from this bottom line that I have over here. The equation for finding A bar is the same, just considering different areas and then multiplying them by the centroid of them to the origin line, which is this bottom line over here, and then dividing them by summation of areas. If you do that, you can see A bar is 2.96 inches. That is the distance from centroid of the whole compression block from this line over here. And now that I know this distance, I can simply add this to this distance and find the distance from the tension and compression force. So Mn, the ultimate strength, will be equal to tension force, this force, multiplied by this distance. And that distance is equal to D. D is this distance. D is always the distance from centroid of steel to the very top of the section, minus A, D minus A plus A bar. This way we can find this distance that we have between the forces. Right? I'm basically multiplying T by the distance between the forces. So calculating that, you can see Mn is equal to 3.71 multiplied by 10 to the power 6 pound inch. Of course it is pound inch because T that we calculated was in pounds and these distances are in inch. So Mn is in pound inch. I have to just present it in cube foot. For that I have to just divide it by 12,000. Final result is about 309 cube foot. That is ultimate strength of this section. If you compare it with the applied loads, you can see 50 cube foot is much lower than the ultimate strength. That's why section was not even cracked under this load. Then 100 just a bit higher than the cracking moment, but it was way below the ultimate strength, and ultimate strength which was about 310 cube foot. At the end of this file, I'm showing you a table, and as you can see in this table, it is basically calculating the moment of inertia about different regions. It is something that you learned from the strength of materials, but just to give you the famous equations and the kind of situations that we have for popular shapes, I'm giving you this table. As you can see, for the rectangle that we used and discussed in this problem, all the equations are given, so it is good to take a look at it or even save it for future examples that we need for finding moment of inertia. Please take the rest of the time and solve this example again at home. Don't just look at what I described. You need to grab a pencil and exactly follow the steps and solve it at home. If you face any question, send me an email and we can definitely discuss it in WebEx meeting.